In this brief lesson, we'll look at proof by contradiction, and specifically we'll prove that root 5 is irrational. So we're asked to prove that root 5 is irrational. So first we will assume that root 5 is rational, and later we'll contradict that statement. So root 5 is rational, that is, root 5 can be written as a ratio, a over b, where b is not equal to 0, and a and b have no common factors, so a and b cannot be simplified. If we square both sides, 5 equals a squared over b squared, and a squared equals 5b squared. So this statement implies that a squared is divisible by 5, that is reasonably obvious, but that also a must also be divisible by 5. It's worth having a closer look at that statement. So a squared is divisible by 5, and a must also be divisible by 5. Here's the first 20 square numbers. The ones that are divisible by 5 are indicated. So if a squared is 25, a is equal to 5, and 5 is obviously divisible by 5. If a squared is 100, a is 10, which is divisible by 5, etc. So that works for all square numbers that are divisible by 5. Let's have it's a sidetrack, but we'll have a look at 3. So the statement would be, if a squared is divisible by 3, a must also be divisible by 3. So again, the first 20 square numbers, the square numbers that are divisible by 3 are indicated. So if a squared is 9, a is 3, which is divisible by 3. If a squared is 36, a is 6, which is divisible by 3. So the statement, a squared is divisible by 3 and a must also be divisible by 3, is true. What about 4? And this is the last one we'll look at. So a squared is divisible by 4 and a must also be divisible by 4. Let's have a look at that. So the first 20 square numbers, all of these are divisible by 4. When a squared is 4, a is 2. Is that divisible by 4? No. It is some of it, so 16 is a squared, a is 4, which is divisible by 4. So it works some of the time, but not all of the time. So if we were to make the statement a squared is divisible by 4 and a must also be divisible by 4, it is not always true. So at that point, our proof by contradiction would break down. And that is what we'd expect. Because if we were asked to prove that root 4 is irrational by contradiction, we would hope that the proof wouldn't work, because root 4 is not irrational, it's rational. So it works for prime numbers. We checked 5 and 3. You can also check 2, 7, etc. It doesn't work for square numbers. And then when you look at numbers such as 6, which are neither square nor prime, it gets a little more complicated, but we'll leave it at there. So back to our proof. This is where we got up to. We ended with the statement a squared is divisible by 5 and a must also be divisible by 5. From that statement, a equals 5r, because a is divisible by 5. Square both sides, and we get a squared equals 25r squared. But we have stated earlier that a squared equals 5b squared. So therefore, equating the two a squared equations, 5b squared equals 25r squared, which implies that b squared equals 5r squared. And we come back to our same point. If b squared is divisible by 5, or it is divisible by 5, therefore b must also be divisible by 5. And we've already investigated that. So now we have a situation where both a and b are divisible by 5. So they have a common factor of 5. But this contradicts our initial assumption that root 5 equals a over b, where a and b have no common factors. So therefore root 5 is not rational. Therefore root 5 is rational, irrational. So that's the entire proof on the screen in front of you. The important parts are here, where we set up our initial conditions, that a and b have no common factors, and then we show that actually they do have common factors, so we have contradicted our assumption. That's why it's proof by contradiction. And the crux, the mathematical crux of the proof is here. So if the proof is to work, then a squared divisible by 5, a is also divisible by 5. As I said earlier, it works for prime numbers. It does not work for square numbers, obviously, and it's a little more complicated when we have numbers that are neither prime nor square. But it's likely you'll only be asked to use the proof for prime numbers.